Hello and welcome to this session. Good morning, my dear students. How are you? And today we are having two sessions in the morning as well as in the evening. In the morning we are going to have the session in which we are going to talk about thermochemistry, and in the evening we are going to have the session in which we are going to talk about the third law of thermodynamics, Gibbs free energy, and the rest of the things which you find quite difficult, although they are not much, but it is found difficult. So, to begin over with it, my name is Anoop Vashishtha. I am an MSc in chemistry from University of Delhi. 26 plus years teaching experience. Lakhs of students have been taught by me, and now it is my turn to teach you thermodynamics. Anything you would like to ask? At this moment, somehow it is not working. My laptop isn't working. I don't know why. Okay, so here it is. So here are 8 students and 6 likes. Could we increase the number of likes, please? Tirthraj, Radhika, Naruto. Well, our regular students are all here, so we can begin over with it. This special session, this is the personal. I believe this would be in a very few times on the YouTube that we have such a one-to-one session going on. So let's begin over with the session, and now we get along with something called thermochemistry. So here we are talking about thermochemistry. In the previous class, we have already talked about the physical thermodynamics. We have talked about the heat capacity. We have talked about the various processes taking place in the physical and the chemical systems. Now, today we are going to talk about, when we talk about thermochemistry, we are talking about, as you can see, the word chemistry here, and thermo means thermodynamics. Here we are going to talk about the chemical thermodynamics. So we are going to talk about the word chemical thermodynamics. Now, what exactly is chemical thermodynamics and how we deal with it? Anybody who has any kind of question you want to ask, you can go ahead and ask me the questions. You can just simply give it in the chat, and I'm going to answer your questions because I have all my eyes on the chat. So, to get along with chemical thermodynamics, let's see what exactly is the difference between chemical thermodynamics and physical thermodynamics. That would be the most important because we have already done physical thermodynamics. Now, this part is something which the students always get confused in, that why is there a different formula and how chemical thermodynamics becomes different from the thermodynamics of physics. In the previous classes, we have done the thermodynamics of physics. Now, we are going to get along with the thermodynamics of chemistry. Now, what exactly it is? Now, when we talk about physical and we talk about chemical. So, when we talk about the physical and the chemical thermodynamics, the very first thing that we need to understand is that in the case of physical thermodynamics, there is no change in bond energies. Clear? And the chemical thermodynamics is characterized by the change in bond energies. Now, you need to remember one thing very clear, very clear. Many of the processes we tell in the normal case, like change of state, is a physical process. That is, no chemical change is taking place. But please be clear, in thermodynamics, change of state is a chemical process because change in state involves breaking and forming of chemical bonds. Weak van der Waals forces, dipole-dipole interaction, hydrogen bond, these also are chemical bonds. So whenever there is a change in these bonds, that is not a physical process, that is a chemical process. Clear? Good morning everybody, Naruto, Radhika. Okay, has the class started, Andina? Yes, the class has started. Clear? So that is what we need to understand. Here, no change in internal energy and enthalpy at constant temperature. Clear? Since we are only talking about the kinetic energy, and if the temperature is remaining constant, there is no change in the kinetic energy. So there is no change in any of these physical, in case of physical thermodynamics, there is no change in internal energy or enthalpy if the temperature remains the constant. But in case of chemical, U and H change due to bonds even if T is constant. Clear? Even if temperature remains constant, there is a change in the bonds, and since there is a change in bonds, the internal energy and enthalpy do change. So that is one thing very clear. And further, moles remain constant. Moles remain constant. And here, moles may change. It's not a compulsion that whenever we have a chemical process, there has to be a change in moles. Has to be is not there. But there may be a change in moles even if the mass remains constant. That is, we are having a closed system, still there can be a change in moles. So that is what we have as the chemical thermodynamics and physical thermodynamics. Now we have a difference. I believe you are writing the notes. Everybody, you are writing the notes. So but just keep telling me that okay, we have written the notes, we have already copied it down, we have understood. I need your responses. Fine. I want to take it as a physical class, that is the class in contact, so that you have that feel. Ritik, no problems if you are late, but you can always watch it again. Now that's what we have as the difference in the physical and the chemical thermodynamics. Now let's talk about a formula. We have a formula, H is equal to U plus PV. Okay. We have delta H is equal to delta U plus delta PV. Okay. We have delta H is equal to delta U plus delta PV. I am not bothered whether I am keeping the temperature constant or pressure constant or not. But one thing is very clear, PV is equal to nRT. PV is equal to nRT. Now here we have the delta H. So delta H will be equal to delta U plus. Now R is a constant that needs to be taken out from this delta. R is not going to change. R delta NT. This we already done in the last class. That's not a problem. I believe you have seen the last class, so there should not be any problem. Now, when we talk about the physical process, we know that N remains a constant, so N can be taken out. It becomes nR delta T in the case of physical process. When we talk about the chemical process, please remember the chemical process are done in such a manner that the change in temperature is not significant, or it can be ignored in comparison to the total temperature. So, delta T is not significant but measurable. So if we have the temperature change, let's say 1 degree, 2 degree, 3 degree, we are talking about the temperature at 298 Kelvin. So 298 Kelvin, the change in temperature is insignificant as compared to 298 Kelvin and the total energy change. So the energy change due to the change in temperature can be neglected. Is it clear? So delta T is not significant but is measurable. And since delta T is not significant but measurable, so all the chemical process, they are done in such a manner that they can be considered isothermal. Please remember, the chemical processes are not isothermal. They are not isothermal, but the change in temperature is such that it can be ignored, and since it can be ignored, the process may be considered, and they are considered isothermal. So what happens is that this T can be taken out from the process, and we get delta H is equal to delta U plus delta N RT. Now, when we talk about this delta N, we are talking about the change in the work. Now, this N is simply the change in the moles of gases. So, here when we talk about delta N is the change in moles of gases. Clear? Liquids and solids are ignored. If we have a reaction in which there are no gases involved, then in that case delta H and delta U turn out to be the same. There is no difference in delta H and delta U for the process in which there is no gas involved. Clear? So, a process or reaction not having any gas, there is no gas, delta H is equal to delta U. Fine. So, this delta N is actually delta N G. When we talk about the equilibrium, when we talk about chemical kinetics, when we talk about chemical thermodynamics, the delta N is the change in the moles of gases. Anything you want to ask here? This part, have you noted it down? With the comments, with the information, have you noted it down? Fine. So, if you have noted it down, now let's talk about a very, very simple thing. Let us say we have a reaction. A reaction is C6H6 liquid plus 15/2 O2 gaseous, giving us 6CO2 gaseous plus 3H2O liquid. Please remember, most often the reactions are being told at 298 Kelvin. At 298 Kelvin, water is a liquid. If somebody tells you that this reaction is taking place at 383 Kelvin, that is 110 degrees Celsius, then in that case, water is going to be a gas. Then you will have to consider it as a gas. But at this moment, I have mentioned water is a liquid. Now, let me get what exactly would be the delta H minus delta U. Can you give me the value of delta H minus delta U in terms of the gas constant R? Okay, so we have R as the gas constant. Now, when we talk about the delta H minus delta U, we know that delta H is equal to delta U plus delta Ng RT. Fine. And here the temperature, let's say T is equal to, for the sake of convenience, 300 Kelvin. For the sake of explanation. So, when we find the delta H minus delta U, that will be equal to delta Ng RT. Is it visible and is it clear, understandable? Delta Ng RT. Now, what is delta Ng? Delta Ng is equal to moles of gases in product minus moles of gases in reactant. So moles of gases in product minus moles of gases in reactant is what we know as the delta Ng. Now here that will turn out to be moles of the gases in product. Please remember this is a liquid. So moles of gases in the product is 6. Moles of the gases in reactant. Please remember this again is a liquid. So this is not going to be considered. It is this. This is the moles of the gases in the reactant. So this is minus 15 by 2. So that turns out to be equal to, I hope you can subtract the fractions, that turns out minus 3 by 2. So delta Ng for this particular reaction is minus 3 by 2. When it is minus 3 by 2, so this particular turns out to be minus 3 by 2 multiplied by R multiplied by 300. And that should turn out to be equal to minus 450 R. So that is the difference between delta H and delta U for this particular reaction. It is a chemical process, it's a combustion reaction. Ritik, it is not 3 by 2, it is minus 3 by 2, and that would make the entire difference, because if you don't put that minus sign, if you are going to get this particular reaction in your exam, please rest assured that you are going to get two values. One is going to be plus 450 R and that another value is going to be minus 450 R. You will get both the values. Or maybe, well, none of these is not actually an option given in any of the examination, but they can do that. And this is going to be the difference between your being in AIMS and being in MAMC. This could be the difference. Or it could be the difference of being in MAMC or some other college, or being in a medical college or nowhere. Could be anything. So don't make such a mistake. This is going to be a very, very silly mistake. Simple thing. And this particular part is not going to require intelligence. Just remember, the person who clears the entrance examination is not the intelligent person, but the person who does not make a mistake. The medical entrance examination is not difficult. It is very difficult. Or very difficult because the student makes silly mistakes. Ritik, magnitude does not make anything. The magnitude means nothing. If you just simply write the magnitude, you are having a wrong answer. So don't justify your writing the magnitude. I never asked you the magnitude, I asked you the answer. Answer was not the magnitude, answer was with the sign. Now you cannot argue with the examiners that okay, I'm just writing the magnitude. They are not going to give you the marks. They are all, of course, going to give you the -1 mark. Now, so this is what we have as the difference. So we have understood what is the difference between physical thermodynamics and the chemical thermodynamics, and now we are going to talk about the various thermodynamics. Now before we get along anything, we need to know how to find the change in any of the energies. To measure heat changes, and the measuring heat changes is called calorimetry. So we are going to talk about calorimetry. When we talk about the calorimetry, what exactly is the meaning of calorimetry? Calorimetry is the measurement of the heat changes in the reaction, whichever reaction we are talking about. Now when we talk about the calorimetry, there is a simple equation. The simple equation is Q, that is the heat change, is equal to MS delta T, where M is the mass, S is the specific heat, and delta T is the change in temperature. Now this is what we have as the calorimetric equation. MS, this can be together termed as heat capacity, which is generally represented as C. Most often it is given to you, and we are going to use this. So this is what we have as a calorimetric equation. This is what is going to be used through and through. Heat change is being measured. Heat change is being determined. The instrument which is used to determine the heat changes is called calorimeter. There are so many kinds of calorimeter. Lot many kinds of calorimeter. But what we are going to talk about is, we are just going to mention two types of calorimeter. Then is, the first type of calorimeter is what we know as the bomb calorimeter. The first thing we talk about is the bomb calorimeter. Talking about the bomb calorimeter, it's a simple device. Here we have a sealed steel container. Sealed steel container. Okay. Now the sealed steel container is insulated. This has an internal container in it. Okay. Now this container is filled with water. Water is being used because water has quite a high heat capacity, and therefore for a large change in energy also, the water does not show a very substantial change in temperature. So this water is responsible for maintaining a constant temperature and keeping it isothermal process. Here we put the thermometer. There is a thermometer out here. Here we have the ignition coil. Here we have the ignition coil. For whatever reaction is taking place, we might need to ignite the reaction mixture. We might need to initiate the reaction. So this is what we have as the ignition coil. And here we might have a stirrer. Now, the representation, the structure might be different, but the basic principle is the same, that we have to have all these things. Now, the reaction mixture is here. The reaction takes place, and the reaction takes place, some energy might be released, might be absorbed. This particular water is going to obtain the change in temperature. We know how much energy is required to change the temperature of this entire system by 1 degree Celsius or 1 Kelvin, and with that we have Q is equal to ms delta T, and we are able to find out the heat. So this is the entire system which we call as the bomb calorimeter. Bomb is actually a sealed container. That is what we call as a bomb. Fine. So that is what we have as a bomb calorimeter. But now when we talk about the bomb calorimeter, you can see that this bomb calorimeter determines the change in heat at a constant volume. So here, volume is constant. So this is what we call as the bomb calorimeter. Should I ask you a question? A bomb calorimeter measures A, internal energy, B, enthalpy, C, work, D, none of these. What does the bomb calorimeter measure? Ignition coil नहीं समझा? बेटा ऋतिक, have you ever talked about car, scooter, bike? That car, scooter, bike has a spark plug. You know that? Every car, scooter, bike, they all have spark plug in them. Diesel vehicles don't have the spark plug, but petrol vehicles do have the spark plug. The CNG vehicles have the spark plug. What is the meaning of that spark plug? Why is it required? Ritik, any idea about that? That is the ignition coil. In this case, the ignition coil has the same purpose, that is to ignite the reaction mixture so that the reaction takes place. Let us say we are talking about the heat release when some amount of petrol is burnt. Now, petrol is not going to burn by its own. It needs some ignition. So, that ignition is provided by the ignition coil. Ananya Sarkar says B, that is enthalpy. Oh, Priyanshu Ghosh says work. But how is it going to measure work? Could you please tell me? Is there any work being done here? Yes, initiate karna, Ritik. That is the same purpose here, ignition coil. Initiate karna reaction ko. Radhika Mittal says work. Not to waste your time, the answer is none of these. It was again a tricky question because enthalpy cannot be measured, internal energy cannot be measured, and work is not being measured. The answer is it measures the change in enthalpy. Or I could have said not enthalpy but enthalpy of reaction. Okay. And very important thing, and here I would like to make some change. The bomb calorimeter does not measure the change in enthalpy. Bomb calorimeter measures the change in internal energy. So even if you talk about the same reaction, if you are saying no sir, we talk about the change, still your answer is wrong because we are talking about constant volume. The change in heat at a constant volume is the change in internal energy. Is it clear? Change in heat at a constant volume is the change in internal energy. Is this clear? Any kind of confusions? It's not B. If you want to say the answer, it should be delta U. You watch the lectures, but you don't learn them. You don't understand the simple nuances. You don't know the difference between internal energy and enthalpy. Internal energy is the change in heat at a constant volume, whereas enthalpy is the change in heat at a constant pressure. Clear? So that was bomb calorimeter. Now let's say we have something else, and that is called a coffee cup calorimeter. A coffee cup calorimeter. In a coffee cup calorimeter, we use coffee cup as a calorimeter. Okay. Priyanshu Ghosh, I told you that we put a lot of amount of water so that it is able to consume the heat, and the change in temperature is not very significant, so that even if we are measuring the change in temperature, still it is considered isothermal. Is that clear? Everybody, you have to do a very high hard work. If you are thinking that you will be able to get 180 out of 180 without doing the hard work, then I am sorry to say you are sadly, very, very sadly mistaken. If you feel that, okay, we have attended the class, it's fine, we are not going to read the notes, we are not going to send the notes, you are not sending the notes on the group. You have ceased to send it. You sent it once and then, okay, fine, we have done our duty. You are not going to do your duty. You have to send your notes every day on the group and you have to do all the questions and you are not doing it. And you feel, okay, बाद में कर लेंगे, बाद में नहीं होगा बेटा, अभी करना पड़ेगा. Ritik, this is not a Hindi medium class. You have to understand in English medium. And if you have a doubt in English, I will be able to explain it once again. I hope my English is simple enough. Okay, why do you need to be sorry? There isn't any sorry. Fine, let's talk about the coffee cup calorimeter. Coffee cup calorimeter is a coffee cup. Okay, it's a coffee cup, and that too a thermocol cup, styrofoam cup, what you can say. This is a normal styrofoam cup. It is filled with the reaction mixture. Okay. We put a thermometer here. The thermometer acts as a stirrer as well. We don't need any other stirrer here. Clear? Ritik, this is not English class. This is English class. Okay. And now what we do is, we put the detergent foam on it. Jhag. Sabun ka jhag. Now this detergent foam it's insulating. It does not allow the heat to pass through. It does not allow any contaminant to go into it. And it works as a frictionless, massless piston. It works as a frictionless, massless piston. And now, the entire process is taking place at a constant pressure. A coffee cup calorimeter, which is a simple calorimeter, you can make it at your home. It requires only one thing, that is a thermometer. Rest of the things are all available. And the reaction mixture, you can talk about the reaction between the dilute acid and the dilute base. You can talk about any of the simple reactions, maybe the reaction, the dissolution of calcium carbonate in a dilute acid, precipitation reactions. You can talk about those reactions easily in this coffee cup calorimeter. And this measures the change in enthalpy. A coffee cup calorimeter measures the change of heat at a constant pressure. So it measures the change in enthalpy. Mayur Bhakra, this particular batch is NEET Elixir batch, and NEET Elixir batch is an English medium batch. I have to be a little strict, isn't it? You have been getting everything that you feel like, okay, teach in English, teach in Hindi, teach in this, teach in that. And you are not making any efforts. This batch you will have to make efforts. Is it clear? I have very few students. I won't even say few students. I have very few students, only 6 students at this moment. And that is also, there also I am quite adamant. Because I want to teach you. I want you to get 180 out of 180. I might be having very few students, but I'll make sure that these very few students are going to get best of the marks. Okay, so that's what we have as the coffee cup calorimeter. Once we have talked about this, I believe you have already written the notes, and today you will have to send the notes to me. Okay, once I finish off the class, send the notes. Having talked about this coffee cup calorimeter, now let's get along with the enthalpy of the reaction. We talk about enthalpy of combustion, enthalpy of precipitation, enthalpy of solution, enthalpy of dissolution, enthalpy of so many reactions. We talk about enthalpy. Now, what exactly is the enthalpy of the reaction? How do we talk about enthalpy of the reaction? Please remember, enthalpy's absolute value cannot be measured. Internal energy absolute value cannot be measured. We can only measure the change in enthalpy. We can only measure the change in internal energy. So, when we talk about the enthalpy of the reaction, that also means the change in enthalpy when reaction takes place. So that is what we have as enthalpy of reaction. The change in enthalpy when reaction takes place is what we call as the enthalpy of the reaction. Radhika Mittal, what is UP per? Upper? Couldn't understand. U is what we call as internal energy. I can't understand what is UPPR. Many times students just write something. According to them it is correct, but it does not make any sense. Okay. Tirthraj, you only are, I am perfectly fine, Afaq. Now, so that's what we call as enthalpy of a reaction is change in enthalpy when the reaction takes place. And once we have talked about the enthalpy of the reaction, we have another word called standard enthalpy of the reaction. Standard enthalpy of the reaction. Naruto, I don't know, UPPR WhatsApp group, how it means that. Well, it's your language, your generation language. I might not be able to understand. मेरे बाल तो काफ़ी सफ़ेद हो चुके हैं, तो शायद आपकी बात मुझे समझ में ना आए. तो just bear with me. Many of the things I say you are not able to understand, so there could be certain things which you say I am not able to understand. So let's talk about the standard enthalpy of the reaction. What is the meaning of standard enthalpy of the reaction? This is the enthalpy change when a complete reaction takes place. So just remember, when we talk about the standard enthalpy of the reaction has to be completed. I'm not talking about the reaction at some in between part. Whatever is mentioned in the reaction equation, that reaction has to be completed. When the complete reaction takes place according to a balanced chemical equation at a constant standard temperature. And please remember, it is usually 298 Kelvin. When we talk about the enthalpy of vaporization, it's at a boiling point. We talk about the enthalpy of sublimation, it's at a sublimation point. If we talk about enthalpy of fusion, it's at melting point. So please remember the temperature is not necessarily 298 Kelvin depending on the reaction, but for other reactions we take the temperature to be 298 Kelvin. Usually 298 Kelvin and a standard pressure, and that standard pressure is 1 bar. So that's what we have as the standard enthalpy of the reaction. हाँ बेटा तीर्थराज मुखर्जी, हाँ हर बारी व्हाट्सएप पर भेजना होगा. Every day after the class you have to send your notes on WhatsApp. Okay, fine enough. WhatsApp ग्रुप बहुत बड़ा हो जाएगा, बहुत सारा उसमें मटेरियल आ जाएगा, कोई बात नहीं, डिलीट मार देना, क्या दिक्कत है. ठीक है ना. It would be nice that you will have the notes of all the other students. Clear? So this is what we have as the standard enthalpy of the reaction. Now one thing you need to understand, it says a balanced chemical equation. It never tells you how the equation has to be balanced. You can balance the equation in many ways. Something like you have an equation H2 gaseous plus half O2 gaseous gives you H2O liquid. Okay. Now the enthalpy change delta H, let's say it is delta H1. Temperature is 298 Kelvin, pressure is 1 bar. So this value is delta H naught, the standard enthalpy. The standard enthalpy of this particular reaction. Further, we can have 2H2 gaseous plus, here now we are going to have O2 gaseous gives you 2H2O liquid. You might argue that these two reactions are same. Quite obviously, here we are talking about the burning of hydrogen in presence of oxygen. So these two reactions are same. The only difference is the balancing of the reaction. But you need to understand that this delta H2 naught, although it is a standard enthalpy, this again is a standard enthalpy of this particular reaction, but these two reactions according to thermodynamics are different. According to thermodynamics, these reactions are different. So these two standard enthalpies are not same. In fact, the second standard enthalpy is twice of the first standard enthalpy. Somebody please tell Kanchan where to send the message for the WhatsApp group. Okay. Somebody give them the link or the number on which they have to send the message so that I can give them the WhatsApp group link. Clear? So here we have the enthalpy change. So this is what we have as the enthalpy change of the reaction. These are the two different reactions as far as thermodynamics is concerned. In case of thermodynamics, for two thermochemical equation to be same, balancing reactants, products, temperature, pressure, must be identical. You change any of these conditions and the reactions are not same. Is this clear? Anyone has any kind of questions here? Now these reactions according to thermodynamics are different. Join the Telegram group, search for my Telegram group and join it. Is this clear? Fine? So here we talk about what is the enthalpy of the reaction. Here we have talked about what is the difference in the enthalpy of the reaction, what is exactly the standard enthalpy of the reaction. Now you need to understand that for each reaction there is some enthalpy change. For each reaction there is some standard enthalpy. And we have so many reactions, and you have just understood that if we change the balancing of the equation, we change the enthalpy. Now an equation can be balanced in I don't know how many ways. So that means for the same reaction we could have so many standard enthalpies, and there are so many kind of reactions. People say that there are a few million compounds, and for each compound at least one reaction would be there, and that many enthalpies would be there. So it is absolutely clear that we cannot study all the enthalpies, so we are going to study very limited number of enthalpies. So let's begin over with the different types of enthalpies. Okay. So let's talk about the different types of enthalpies. The very first thing that we talk about is what we call as the standard enthalpy of formation, which NCERT has mentioned as delta FH. Now NCERT has put theta over it. In certain books it's V because of the change in the fonts, in the printing mistake. So it might be theta, it might be 0. It's actually referred to as delta formation H, not NAUGHT, not standard. So that means standard. So that is how NCERT has represented the standard enthalpy of formation. Now what exactly is standard enthalpy of formation? We need to know the definition. Standard enthalpy of formation is the enthalpy change when a pure substance. Now when you talk about the pure substance could be an element or a compound. Now you might say, sir, how can we talk about the element being formed? Can element be formed? Yes, elements can be formed when we talk about the different allotropes. We can talk about the formation of diamond from graphite. We can talk about the formation of graphite from diamond. We can talk about the formation of ozone from oxygen and oxygen from ozone. Ozone is also element, oxygen is also element. They are the pure substance. They are not compound. Ozone is not a compound. It's an element. It's an allotrope of the same element. We can talk about the conversion of white phosphorus to red phosphorus to black phosphorus. We can talk about the conversion of rhombic sulfur to monoclinic sulfur and monoclinic sulfur to rhombic sulfur. So we are getting the element. Okay, and so many compounds are there, I don't need even to tell you. So that is what we can have. The enthalpy change when a pure substance is not a mixture, it is an element or a compound, is formed from its constituent element or elements in their respective standard state at 298 Kelvin 1 bar. So, standard enthalpy of formation is the enthalpy change when 1 mole of when 1 mole that I missed. If I miss it, that's going to be wrong. Yes, white phosphorus is dangerous, Sumit Roy. No doubts about that. Okay. So, enthalpy change when 1 mole of a pure substance, that is important thing, is formed from its constituent elements or elements in their respective standard state at 298 Kelvin 1 bar. So, that is what we call as the standard enthalpy of formation. Now, there comes a definition called the standard state. Standard state. Standard state is the state in which a pure substance is obtained most conveniently at 298 Kelvin 1 bar. Here you need to understand that the standard state does not mean the most stable or most unreactive state. No, it does not mean that. The standard state means the pure substance must be obtained. That is the standard state. So, when you talk about the standard state here, many of the people have a tendency to say the standard state is the most stable state of the substance except for this. Why do we put an exception? Why can't we simply define that the standard state is the one which is obtained most conveniently? Like the typical exception they quote is white phosphorus. White phosphorus is not the stable form of phosphorus, but it is the standard state because white phosphorus is obtained the first. It is the purest form of phosphorus and we get the red and the black phosphorus from white phosphorus. So, that is why white phosphorus is considered to be the standard state of phosphorus. But then white phosphorus is more reactive. Now, when we talk about diamond and graphite, graphite is the standard state of carbon, although diamond is a little less reactive. Still, so is it not better to say that the standard state is the state in which we obtain the pure substance most conveniently rather than saying this is the most stable state? This doesn't have any exception. Those might be having exceptions. So, the standard state of phosphorus is white phosphorus. For carbon, it is graphite. For iodine, it is solid. For chlorine, it is gaseous. For bromine, it is liquid, because at 298 Kelvin 1 bar, bromine is a liquid. Bromine has a boiling point of 35 degrees Celsius. So, at 298 Kelvin, it should be a liquid. A volatile liquid, agreed, but a liquid nonetheless. So, that is what we have as the standard state at 298 Kelvin 1 bar. Sulfur, it is rhombic sulfur. Oxygen, it is O2. Hydrogen, it is H2 gaseous. So, these are the standard state of the various substances, and this is the standard enthalpy of formation. Remember this definition thoroughly. Okay. Now, let's have a few simple, very simple question. Half H2 gaseous plus half Br2 gaseous gives us HBr gaseous. Okay. The enthalpy, standard enthalpy of this particular reaction, generally we write it delta RH naught, is, let's say, Y. Now tell me, is Y the standard enthalpy of formation of HBr or not? Is Y the standard enthalpy of formation of HBr or not? Yes or no? Ritik, yes, pure substance. 1 mole of the pure substance is being formed. Nitrogen? There is no nitrogen here. Okay, nitrogen gaseous is the standard state, no doubts. Is this the standard enthalpy of formation of HBr? Ananya says no. Rani Sahu says yes. Ananya, why did you say no? Ritik said yes. Ananya, you said no. Why no? Everybody is saying yes. Is this the standard enthalpy of formation of HBr? Yes or no? Munna Kumar says, Ji sir. That's okay. That is the condition. I have said this is a standard enthalpy of reaction. Standard enthalpy of reaction. So this is 298 Kelvin. This is 1 bar. So what? Tell me. Yes or no? Priyanshu Ghosh says no. Now Priyanshu Ghosh no should become yes. That is the thing, that even if you complete the course, you know the course thoroughly, you make a question wrong. It should be liquid. The standard state of bromine is liquid, not gaseous. This is not the standard enthalpy of formation of HBr. And then I have written 1 bar. I told you, bromine standard state is liquid, not gaseous. Now this is what we have, a standard enthalpy of formation. Similarly, if I write H2 gaseous plus I2 gaseous gives us 1 by 2 of this, 1 by 2 of this, HI gaseous at 298 Kelvin, 1 bar. This again is not the standard enthalpy of formation because iodine should be solid. A very simple question, absolutely within your course, absolutely given in NCERT, absolutely explained to you, and you might make a mistake in the examination because you forgot that bromine has to be a liquid. Nahi Sakshi, I will not provide you the telegram, the PDF, because I don't have the PDF. You have to make the notes from the lecture. You have to make the notes from the lecture. I am talking about here 180 out of 180 in chemistry, and I cannot give you the crutches. मैं तुम्हें बैसाखी नहीं दे सकता. Quite obviously, if you want to get the notes, you can get it from the students. Those students have made the notes. You can take their notes if you wish to. They are much better than what I am writing. But that would be crutches. It will be better if you make your notes. Giving those notes, these notes to you on Telegram, that's not a big deal. Okay? Of course, I am writing it. What's the big deal in just converting into a PDF and sending it to you? So that's what we have as the standard enthalpy of formation. Anyone has to ask anything? Anyone has to ask anything? Any confusions here? I have very few students and it appears you are not doing the required amount of hard work. I just told you and you would make a mistake. Now we get along with something called the standard enthalpy of combustion. Okay, most often represented as delta CH naught. Standard enthalpy of combustion. हाँ ऋतिक, हमको देखना होगा कि प्योर सब्सटेंस किस स्टेट में होगा. यही देखने के तो मार्क्स मिलते हैं. वो कहते हैं ना कि ये काम करने के पैसे मिलते हैं, तो यहां पे यही देखने के तो मार्क्स मिलते हैं. आपको क्या लगता है 40 सेकंड के अंदर या 1 मिनट के अंदर अगर आपको कोई क्वेश्चन करना है तो उस क्वेश्चन के अंदर आप ये भी नहीं देखोगे उस क्वेश्चन में लिखा क्या है? क्या उसके अंदर 10 घंटे लगते हैं, 10 मिनट लगते हैं? क्वेश्चन भी ठीक से नहीं पढ़ोगे क्या? दैट्स व्हाट मेक्स द डिफरेंस. The person who does not make a silly mistake gets 720 out of 720. The person need not be intelligent. Yes, as like offline classes, this is even better than the offline classes because here we are actually interacting with each other. You are sitting at your home, you are not wasting your time, you are making your notes and your notes are being checked. बट आई कैनॉट, बस एक काम नहीं कर सकता ऑफलाइन क्लास वाला, मैं तुम्हारा कान पकड़ के नहीं घुमा सकता, बाकी तो मैं सब कुछ कर दूंगा. ओके, यस, नो, व्हाट डू यू मीन बाय ऋतिक? सो इफ वी टेक Cl2, Cl2 is gaseous, Sumit. Who said that if Br2 is a liquid, Cl2 has to be a liquid? Br2 is different, Cl2 is different. And each element, each substance has its own standard state which is not dictated by any other substance. If I have diamond and graphite, graphite is the standard state. That does not mean that sulfur is also going to be diamond. Or oxygen is gaseous, O2, sulfur does not stay in S2. कमाल है. ठीक है? So let's talk about the standard enthalpy of combustion. Standard enthalpy of combustion is the enthalpy change. Please remember enthalpy change. When 1 mole of a pure substance, enthalpy of combustion, enthalpy change when 1 mole of a pure substance is completely burnt in excess of air or oxygen. Excess is important. Carbon converting to carbon monoxide is not excess of air. So carbon converting to carbon monoxide is not enthalpy of combustion. मुन्ना कुमार, डांट सकता हूं तो क्या होगा? तुम उठा के उसको बंद कर दोगे, म्यूट कर दोगे, क्लास छोड़ के चले जाओगे, मैं क्या कर लूंगा? डांट तो मैं सकता ही हूं, डांट तो तुम्हें हुई, वो तो तुम्हारे हर क्वेश्चन के साथ डांट फ्री मिलती है आंसर के साथ. So enthalpy change when 1 mole of a pure substance is completely burned in excess of air or oxygen at 298 Kelvin 1 bar. That is what we call the standard enthalpy of combustion. 1 mole of a pure substance. That is important. Clear? And what decides excess? What decides excess? Like, if I write H2 gaseous plus half O2 gaseous gives us H2O liquid at 298 Kelvin 1 bar, will this be considered as the standard enthalpy of combustion? I have written half O2. Will this be standard enthalpy of combustion? Yes or no? आंसर दो यार, कहां खो गए? फिर डांट खानी है क्या? आंसर. Standard enthalpy of combustion. Is it standard enthalpy of combustion of hydrogen or not? Yes, this is standard enthalpy of combustion, because this half only talks about how much oxygen hydrogen is going to react with. It is not telling you how much oxygen is present in the reaction. Oxygen is in huge excess. This is the amount which is being consumed. Fine. Even if you have huge amount of oxygen, it does not mean that oxygen consumed will become more. The equation will be balanced in this manner only, whatever be the amount of oxygen present in the reaction. Is this clear? So that is what we have as the standard enthalpy of combustion. Now, one thing you need to understand: combustion is always exothermic. When we talk of exothermic, that means delta H is always negative. See, when we talk about the exothermic reaction, it so happens that the system releases energy. So, substance's energy decreases. So, the net change in enthalpy of the system is negative. We always see that whenever we have an exothermic reaction, the temperature rises. The temperature rises because when the energy is released, it first of all gets converted into kinetic energy. That is the temperature. And then it comes to the temperature of the surrounding and the energy is lost. System's energy decreases. Initially, the temperature increase is observed in the exothermic reactions. Clear? So, if there is a combustion reaction or reaction with oxygen which is endothermic, that will not be a combustion reaction. And the example for that is, let's say we have N2, half N2 gaseous plus half O2 gaseous gives us NO gaseous. Now here delta H is positive. It's an endothermic reaction. So this is not combustion. This is not a combustion reaction. Anybody who's not liked, just go ahead and like the session. Clear? Similarly, if we talk about something like half O2 reacting with F2 gaseous to give OF2 gaseous. Now that again is not a combustion reaction. Is this clear? नहीं ऋतिक, मोल से कैसे पता करोगे? How are you going to find out with number of moles कि it is exothermic or endothermic? This reaction is endothermic and C solid plus half O2 gaseous gives you CO gaseous is exothermic. I can't understand that. How are you going to relate it to number of moles? Now, C solid plus O2 gaseous gives you CO2 gaseous, again is delta H equal to negative. Here is 1 mole, here is 1 mole, here is half mole, here is 1 mole. How can you relate? Mr. X, Miss X, whoever it is. So you have got the name of Twitter now, X. I don't know what Elon Musk was thinking to name Twitter as X. So that's what we have as standard enthalpy of combustion. Now here comes a very peculiar thing, and that very peculiar thing is, sir, I have a big problem while writing equation. Why do you write equation? You are not supposed to write equation. Equation exist. You don't write them. You observe them. Clear? ऋतिक, आपको कैसे पता चलेगा किस बिजनेस में प्रॉफिट होगा, किस में लॉस? बिजनेस करके पता चलेगा ना. In the same manner, we have observation that the reaction is exothermic or endothermic. I told you in the very beginning that thermodynamics, kinetics, equilibrium, physical chemistry, all things are observed. They are not predicted. कैसे पता चलेगा? नहीं पता होता है. फिजिकल केमिस्ट्री है ये, और केमिस्ट्री इज ऑब्जर्वेशन. Chemistry is not prediction, it is observation. Okay, so that's what we have as enthalpy of combustion. And now we need to understand that combustion reaction, does it take place at 298 Kelvin? We need to provide some energy to initiate a combustion reaction, and while combustion reaction is going on, it's an exothermic reaction. The temperature is bound to rise, the pressure is bound to increase, and then it comes back to the original position. Then how can we talk about 298 Kelvin? And here comes a very famous observation, again observation, and that's what we call as Hess law of constant heat summation. The Hess law of constant heat summation. What does it mean? It is based on the simple fact enthalpy is a state function. Enthalpy is a state function, so enthalpy change, whether it takes place in a single step or multiple step, or it takes place in a single reaction, multiple reactions, it will remain the same. Okay, so it simply means a reaction, whether takes place in any number of steps, the enthalpy change is same till initial and final position are same. Is this clear? So you find the enthalpy change is same. Okay, so you do what you need to do. Okay, our class is going on. Any kind of confusions here? Clear? So that is what we have as the enthalpy of the reaction. enthalpy of combustion, or Hess law of constant heat summation. Now we can talk about a question, a simple question, a very, very important simple question. And with that, we are going to talk about how we are dealing with thermochemical equation. Calculations with thermochemical equations. Calculations with thermochemical equations. Let's talk about that. Let's have a question. Delta C H naught graphite is equal to it is कितना है -393 kilojoule per mole. Okay. Delta CH hydrogen is equal to -342 kilojoule mole inverse. Okay. Ananya, we are going to get the break after this particular question. Okay, 3 minutes break. Okay. I'll write the question and then I'm going to give a break and then we are going to solve the question after 3 minutes. Delta CH2 is this and delta C H naught glucose is equal to -1500 kilojoule mole inverse. Okay. Find delta formation H naught glucose. Okay. So this is the question you have, and I am going to give you a break of 4 minutes. You can start at 11:30. So you get a break of 4 minutes. पानी पी लो, खाना खा लो. नहीं, पानी पी लो, खाना नहीं खा सकते तुम अभी. 4 minute break. Okay, 4 minutes. 11:30 we are going to start the class again. Meanwhile, solve this question. Okay, so I am here. Are you there? Timer is here and I am here. So to begin over with it, so we are solving this particular question. So let's begin. How do we solve it? See, we have the enthalpy of combustion of graphite. C, graphite, I am putting it capital G, plus O2 gaseous gives us CO2 gaseous. That is the enthalpy of combustion of graphite. So this value is minus 393. I am not writing very nice value. So here we have hydrogen. Enthalpy of combustion of hydrogen, gaseous plus half O2 gaseous gives us H2O liquid. Now this value is minus 342 kilojoules per mole. And then we have enthalpy of combustion of glucose. Here we have C6H12O6 solid plus 6O2 gaseous gives us 6CO2 gaseous plus how many? 6H2O liquid, and the energy change is minus 1500. Okay. Now these are not exact values. I have not seen it from any book. Clear? This is an equation 1, this is the equation 2, and this is the equation 3. The equation that we require is the standard enthalpy of formation of glucose, and standard enthalpy of formation of glucose would mean that we have the elements on the left hand side. To get the elements on the left hand side, the equation would be I need 6 carbon, so it is going to be 6C graphite. I need 12 hydrogen, that would mean 6H2 gaseous, and I need 6 oxygen, that would be 3O2 gaseous, and that would give me C6H12O6 solid. So that would be the equation of enthalpy of formation of glucose. Ritik, again you are giving the magnitude or you are giving me the value? Now, to get 6 carbon, I need to get the first equation 6 times. The first equation must be 6 times because here I need 6 carbon. To get 6 hydrogen, I need to make second equation 6 times. Okay? And to get C6H12O6 on the right side, I need to subtract the third equation. समझ आया? ऋतिक, गर्दन घुमा दूंगा बेटा मैं तुम्हारी, फिर तुमने वही गलती कर रहे हो. Are you giving me the magnitude or you are giving me the value, the particular actual with sign? This will be 6 into minus 393 plus 6 into minus 342 minus 1500. बेटा साइन में मिस्टेक कुछ ज्यादा नहीं हो गई? Can you get the value of here? Any problems here? So that is how we are going to deal with the thermochemical equation. ऋतिक, अगर तुमने ये कर दिया तो फिर तुम देयर इज नथिंग टू बी प्राउड ऑफ दैट कि मैंने ये कर दिया. ये नहीं करना था ना. Anybody has any kind of confusion in this part? तीर्थराज -2820 बता रहे हैं. ऋतिक -2730 बता रहे हैं. Even the values are different. Recheck. Ananya -2820. Whoever has not liked the session, please like it. Ritik, check your calculation. Everybody else is getting 2820. Fine. So those are what we call as the thermochemical equations. Okay. Now once we have talked about the standard enthalpy of combustion, standard enthalpy of this, we can have so many other enthalpies. So many other enthalpies. Okay. Now let's have something called the standard enthalpy of neutralization. Standard enthalpy of neutralization. Okay. ऋतिक, ये यार मैं फिर गलत किया इज नथिंग टू बी प्राउड ऑफ. क्यों गलत किया? क्यों गलत किया? और एग्जामिनेशन में देन यू विल से सर मैं सब कुछ करता हूं, मेरे मार्क्स नहीं आते. पता चल रहा है क्यों मार्क्स नहीं आते? एंड देन यू पुट द ब्लेम ऑन एवरीबडी. मेरे से तो होगा ही नहीं, मैं तो कर ही नहीं सकता, मुझसे तो होना ही नहीं है, मेरे तो मार्क्स ही नहीं आते, मैं सब कुछ करता हूं, मार्क्स नहीं आते. क्यों क्यों नहीं आते मार्क्स? ये नहीं आते. So let's talk about the standard enthalpy of neutralization. Standard enthalpy of neutralization would mean the enthalpy change when one equivalent of strong acid. When we talk about one equivalent of a strong acid, it simply means 1 mole H plus is neutralized by one equivalent of strong base. Now when I say strong base, it is 1 mole of OH minus at 298 Kelvin, 1 bar in sufficient dilute solutions. Sufficient dilute solution would mean that they are completely dissociated. That is, 1 mole of H plus is completely dissociated, 1 mole of OH minus is completely dissociated, so that the standard enthalpy of neutralization is actually this enthalpy. For any strong acid, for any strong base, this will be the reaction. Okay? For any strong acid, for any strong base, this would be the reaction. So, this reaction is the same, whatever be the reactant, whatever be the acid, whatever be the base. And that is why the delta neutralization H naught is a constant. Normally, we write it as minus 57.2 kilojoule mole inverse. Is this clear? So, that is what we have as standard enthalpy of neutralization. Any doubts here? Anyone has any kind of doubts? हाँ बेटा ऋतिक, this constant is fixed. The same value is used for all strong acids and all strong bases. I agree that when we talk about specific acid and specific bases, the value is going to be different from this, because all acids and all bases are not completely dissociated at that particular temperature and concentration. But still, this is the value which is considered. Now we have enthalpy of phase transition. The standard enthalpy of phase transition. Now, phase transition could be the change in state, could be change in phase, could be dissolution, could be conversion of one allotrope into another. So, that's what we could have, the standard enthalpy of phase transition. So, when we talk about the phase transition, it is enthalpy change when 1 mole of a pure, not necessarily pure, fine pure substance changes from one phase to the other at phase transition temperature and 1 bar pressure. The phase transition temperature is not necessarily 1 or 298 Kelvin. It could be something else as well. Okay. The phase transition temperature could be different from that 298 Kelvin. It could be different, and it is mostly different. Clear? A phase transition could be delta fusion H naught. Now, this is what we call as standard enthalpy of fusion. The standard enthalpy of fusion. Now, standard enthalpy of fusion is the enthalpy change when 1 mole of pure solid converts to liquid at its melting point and 1 bar. So that's what we have as the standard enthalpy of fusion. Clear? And just remember, at 1 p.m. we are having the launch of our Plus course. So if anybody who has not joined with the Unacademy app, download the Unacademy app, use the code AVLIVE and join with us. Is it clear? So just don't forget it. So that's what we have a standard enthalpy of phase transition. This is fusion. And in the same manner, I can have enthalpy of the vaporization. The standard enthalpy of vaporization would be just having the boiling point here. And it would be, ऋतिक फिजिक्स टीचर आ जाएंगे बेटा, क्या जल्दी है? अभी तुम केमिस्ट्री तो पढ़ लो पहले. केमिस्ट्री पढ़ो, बॉटनी पढ़ो, जूलॉजी पढ़ो, फिर फिजिक्स भी पढ़ लेना. So this is what we have a standard enthalpy of fusion. Then we could have delta vaporization. We can have delta sublimation. Sublimation is solid to vapor at sublimation point. Okay. Delta H vaporization is conversion of liquid to vapor at boiling point. Is this clear? So that's what we have a standard enthalpy of phase transition. It could be the conversion of diamond to graphite, graphite to diamond. It could be sulfur rhombic to sulfur monoclinic. Those also are the phase transition. Clear? Having talked about the phase transition, let's talk about two very important concepts. And those two very important concepts are the lattice energy and the bond energy. Okay. First of all, we talk about the lattice energy. Lattice energy. You can write it as delta lattice H naught. Okay. Now please remember, lattice is for crystalline solids. Crystalline solids. It is not for amorphous substances. We don't talk about lattice for amorphous substances. Okay. So lattice energy is enthalpy change when 1 mole crystalline solid, 1 mole crystalline solid, it could be molecular solid, it could be the ionic solid, it could be metal, it could be anything, it could be any crystalline solid, not amorphous. Clear? When 1 mole crystalline solid is converted to its constituent atoms for elements. When we talk about metals, When we talk about carbon, we talk about graphite, we talk about diamond, we talk about boron, we talk about silicon, atoms. That would be the lattice energy. Molecules. Molecules is for molecular covalent solids or ions. Ions is for ionic solids. At 298 Kelvin, 1 bar is termed as the standard lattice energy or simply lattice energy. Please remember, lattice energy is always positive, means endothermic. I don't care what you have read. Many people might say that it is the energy absorbed or released. No, it is always absorbed. It is like conversion of the solid to the gaseous or gaseous to the solid. No, it is always solid to the gaseous. Okay, that is how NCERT has defined the lattice energy, and that's what we are going to follow. If another book says, सर उस किताब में तो लिखा हुआ था, सर उन्होंने तो ये बताया था, उन्होंने ये कहा था, भाई मुझे नहीं पता वो सही है या गलत है, मुझे सिर्फ इतना पता है कि ये एनसीईआरटी में लिखा हुआ है, जो एनसीईआरटी में लिखा हुआ वो हमें मानना है, सही या गलत कोई मीनिंग नहीं रखता. Is this clear? So that is what we have as the lattice energy. Now lattice energy is an extremely important part because the existence of any solid is because of the lattice energy. Fine. And when we talk about the ionic substances are formed because of the lattice energy. Any kind of doubts, anybody? Okay. So that's what we have as a definition of lattice energy. Now we are going to get along with something called the bond energy. Bond energy. Now we are going to understand the bond energy in a little way थोड़ा सा घुमा के understand करेंगे. Let's say we have methane, CH4. Okay. We provided some energy and we convert it into CH3 plus hydrogen. The energy change could be written as delta H1 or delta 1H, whatever you wish to write it as. Then we provide energy to CH3, convert it into CH2 plus H. Now the energy change is delta H2. Fine. Then we have CH2 converting to CH plus H. This is delta H3. Then we have CH converting to C plus H. This is delta H4. Okay. Now each of these energies are bond dissociation energies. These are bond dissociation energies and these are different energies. These are not equal to each other. They are different. Fine. They are different because the reactant and products are different. They are not thermochemically the same. Let's add them. If I add them, I get CH4 gets C plus 4H. Now this becomes delta H total. Now this is delta AH, that is enthalpy of atomization. Clear? If I divide the delta H total by 4, that is the number of bonds I have. Now this is the average bond dissociation energy which is most often considered the bond energy. That is the average of the similar bonds is termed as the bond energy. Any confusion? Any problems? In the evening class at 4 p.m, initially we are going to talk about the NCERT, that is we are going to talk about the entire thing about this thermochemistry, the NCERT, and then once we have talked about the NCERT, we are going to get along with the third law of thermodynamics. That is going to be there in the evening, and today at night we are going to have a special class in which we are going to do questions of thermodynamics. Clear? The objective questions of thermodynamics. So today we are going to finish off with thermodynamics. I hope you are able to bear with it. Till the time your physics doesn't start, I believe you can take the advantage of chemistry being done in such a manner. Okay. So that's what we have as the average bond dissociation energy. This is what we call as the bond energy. Hoga Ritik? Tomorrow also we are going to have the morning class. We have not yet finished off all the chapters. We have so many chapters to do. Okay. We are going to have these rapid classes till 1st August. Then we are going to have the cool down. Okay. कोई बात नहीं ऋतिक, जितना अटेंड कर सकते हो उतना अटेंड करो. Anybody who has not liked the session as yet? But I believe everybody has liked. We have already very few students. So this is what we call as bond energy. Now let's have the question of something called the Born-Haber cycle. Born-Haber cycle. Born-Haber cycle is the diagrammatic representation of all enthalpy changes. That is all steps in a reaction. Many people think that Born-Haber cycle is something to be learned, something to be created, but no, Born-Haber cycle is actually a tool so that you don't make a silly mistake in the reactions. Clashing Arena says, sir, my second drop started but still want to crack AIMS Delhi. But your want needs to be backed up by your hard work. Clear? You might want anything, but are you working for it? Can you work for it? To convert your wish into your destiny, you have to work very hard. Okay. So here we have the Born-Haber cycle, which is diagrammatic representation of all enthalpy changes, that is all steps in a reaction. That is what we call as the Born-Haber cycle. For example, we talk about the enthalpy of formation of sodium chloride. Now, this is a very common example used in all the books because it uses all the things that we have studied. So, we have delta FH naught NaCl. Delta FH naught NaCl, sodium chloride. So, we have sodium solid, that's the standard state of sodium, reacting with half Cl2 gaseous. This is the standard state of chlorine, giving us NaCl solid. This is the state of sodium chloride, and the energy change of this reaction is delta H F NaCl naught. Now, this is the reaction that we have. Now, once we are talking about this reaction, there are so many steps in this reaction. Let us see what are the various steps in this reaction. The first step in this reaction, as far as sodium is concerned, I have to provide it delta AH naught of sodium. That is enthalpy of atomization of sodium, or you may call it enthalpy of sublimation. For metals, enthalpy of sublimation, enthalpy of atomization, and the lattice energy, they are the same thing. Clear? So, this gets converted into Na gaseous. Now, these are the ionic compounds. So, sodium consists as Na plus. To convert sodium into Na plus, I need to provide a further energy, and that further energy is what we call as the ionization energy of sodium. When I provide the ionization energy of sodium, this sodium gets converted into Na plus, again that is in the gaseous state. So, that is to do with sodium. Now, chlorine. I want to convert the chlorine into Cl gaseous, chlorine atom. You may call it enthalpy of atomization, or this enthalpy of atomization can be considered as half bond energy of chlorine-chlorine bond. Half of the bond energy, because the bond energy is breaking off 1 mole of the bond. Bond energy is always endothermic. Clear? Now, again chlorine needs to be converted into ion. So, this needs to be converted into Cl minus gaseous. Now, the Cl minus gaseous, the energy change is going to be delta electron gain enthalpy of Cl. We are providing the electron to the chlorine, so it is electron gain enthalpy of chlorine. Fine enough? These two react, they convert to sodium chloride solid, and now the energy is being released out because we are converting the gaseous ions into the solid, and so here the energy change is minus of lattice energy. Minus of lattice energy, because energy is released out where it should have been absorbed. So, it is opposite of lattice energy, so it is minus lattice energy. So, the total energy change is all the energy sum, whatever is written in the Born-Haber cycle, you just have to add those energies. You do not have to talk about anything else, you just simply have to add those energies. And those energies would mean delta FH naught NaCl is equal to delta AH naught Na plus ionization energy of sodium plus 1/2 bond energy of Cl2, okay, plus delta electron gain H naught of chlorine minus lattice energy. Any kind of confusion? And this is what we call as the Born-Haber cycle. I hope you are able to understand whatever we have done in this session today. Anything you would like to ask? So here is unlock biggest offer, and we have the next session at 1 p.m. Remember, we have the session at 1 p.m. Then we have the session at 2 p.m., 3 p.m., 4 p.m. And then evening sessions would start. That is on the special classes. So you have to unlock your biggest offer. That is limited period offer. Subscribe, use the code AVLIVE. 25% off on all Plus and Store subscriptions. Just use the code AVLIVE to get any of these subscriptions. This mega sale week is here. Iconic prices slashed by 15%, extra 25% off. Get NEET UG Assure also. Just you can go through it. What exactly is NEET UG Assure? And this is target NEET UG 2024 is 40, instead of 65,499, it is 41,755. And here, target NEET UG is, instead of 98,999, it is 63,111. So that's the huge offer, 15 plus 25. हाँ ऋतिक, बाकी इसका क्लास इवनिंग में होगा. So 2 p.m. you have Swati Batra ma'am with Botany, 3 p.m. you have Sachin Kapur sir with Zoology, 4 p.m. again I am with you for Chemistry. These all sessions are going to be there, and 1 p.m. we have a special session at the launch of the Plus courses. Okay, join our channel, YouTube and Plus NEET Elixir by Unacademy. Join with us, and here you have NEET UG subscription. Go ahead, use the code AVLIVE. Download the Unacademy app if you have not downloaded as yet. Select your goal and view subscription. This is my page on Unacademy, unacademy.com/Anoop Vashishtha. You can just simply join there and be with me. Like, subscribe, share and comment. You have to do that. Subscribe the NEET Elixir by Unacademy for the best live classes. Like, share, subscribe. Thank you. मिलते हैं आपसे 1 बजे. किसी को कोई डाउट, any confusions, anything you want to ask? Great Ritik, ऑफलाइन क्लास लगा, मजा आ गया, डांट भी पड़ गई. ओके, मिलते हैं आपसे 1 बजे. बाय बाय, टेक केयर.